Right now, at the top of the Burj Khalifa, the tallest building on Earth, the floor is moving. Not from an earthquake, not from an explosion, not from any structural failure, just slowly, silently swaying. On a normal windy day, the very top of that building shifts nearly 2 meters in either direction, back and forth, continuously, and every single engineer who designed it knew that would happen because they calculated it, planned for it, and deliberately built it that way. Here is the paradox at the center of every modern skyscraper on Earth. The harder you try to make a building resist movement, the stiffer the steel, the more rigid the frame, the more likely it is to fail, to crack, to come apart. And the buildings designed to sway the most, those are the ones standing 60 years later in typhoon zones on earthquake faults, completely intact. This is not a compromise. This is not a flaw in the engineering. This is the single most sophisticated trick hidden inside modern construction. And it is happening right now above millions of people who have no idea. To understand why skyscrapers are built to move, you first need to understand what wind actually is and how completely it changes at altitude. At street level, wind is chaotic. It bounces off buildings, trees, and parked cars. It loses energy to friction with the ground. It arrives at a building's base in irregular, low-power gusts. At 400 meters above the ground, none of that friction exists. There are no obstacles, no surface roughness. The air moves in massive, organized, continuous flows. And this is where the physics become extraordinary. Wind force does not increase proportionally to wind speed. It increases with the square of the speed. Double the wind speed, 4 times the force. Triple the wind speed, 9 times the force. The upper floors of a 500-meter building are experiencing wind pressure that is 9 to 12 times greater than anything at the base. We are talking about a lateral force equivalent to hundreds of millions of kilograms pushing against the building's side. Every second that building stands, the obvious instinct and the wrong answer is to build the structure rigid enough to resist all of that force, to make the steel so thick and the frame so stiff that nothing can push it at all. And this is exactly where engineers discovered a problem no one fully anticipated. On November 7, 1940, a newly built suspension bridge in Tacoma, Washington, began to oscillate. The wind speed was 64 kilometers per hour. Not a hurricane, not a record, a moderate, unremarkable wind that bridge engineers of the time would have considered well within acceptable limits. But that wind had a specific property. Its gusts were arriving at a frequency, a rhythm, that matched the bridge's natural frequency, the rate at which the structure naturally wanted to vibrate when disturbed. When those two frequencies synchronized, the bridge did not resist the energy. It absorbed it. Each gust added to the oscillation instead of canceling it. 4 hours later, the Tacoma Narrows Bridge collapsed into the water below, killed by a moderate wind because of a single invisible match: frequency alignment. Every structure on Earth has a natural frequency. Push it and release it. It oscillates at a predictable rate. A wine glass has one, a guitar string has one. Every skyscraper has one too. Short, rigid buildings have high natural frequencies. They vibrate fast. Tall, flexible buildings have very low natural frequencies. A single back and forth cycle at the top of a super tall skyscraper can take 8 to 12 seconds. It is barely perceptible, but it is continuous. If the wind arrives at a frequency that matches the building's natural frequency, you get resonance. Not an immediate collapse, but sustained, accumulating oscillation. Structural fatigue, connection loosening. Over time, in extreme cases, failure. The engineering problem is stark. You cannot control what frequency the wind arrives at. Wind is chaotic. Wind changes. But you can control the building's frequency. And you can control what happens when it moves. The correct solution, when engineers first proposed it, sounded wrong. Don't make the building more rigid. Make it more flexible. A flexible building naturally shifts its resonant frequency away from any fixed wind frequency. Instead of storing dangerous energy as internal stress, it moves, a slow, controlled sway that disperses the force across the entire structure. But flexibility creates an entirely different problem: the occupants. Engineers discovered that the threshold at which a building can safely sway is far above the threshold at which human beings become uncomfortable, disoriented, and frightened. The Burj Khalifa can sway 1.8 meters at its tip with zero structural risk whatsoever. But a person sitting at a desk on the 160th floor, feeling that slow rolling movement under their feet, will not think about structural calculations. They will think the building is falling. The engineering goal became allow the building to move enough to stay safe from resonance, but reduce that movement enough that the people inside don't notice. And the device that solved both problems at once is one of the most elegant pieces of engineering ever built. The tuned mass damper, known in engineering as a TMD. In concept, it is a counterweight, a massive object suspended inside the building near its top, calibrated to swing in the opposite direction from the building whenever wind pushes it. When the building moves right, the mass swings left. The opposing momentum partially cancels out the sway. The building still moves, but far less than it would without it. The engineering term is damping. The reduction of oscillation amplitude over time, the transformation of dangerous repetitive energy into manageable, controlled motion. The word tuned in tuned mass damper is the critical part. The suspended mass must oscillate at a frequency that is precisely matched to the building's natural frequency. If the calibration is off, if the mass swings too fast or too slow relative to the building, it doesn't reduce the oscillation, it amplifies it. Getting the tuning wrong doesn't just fail to help, it makes the situation worse. The most famous example in the world sits inside Taipei 101 in Taiwan, between the 87th and 91st floors. Suspended from 16 steel cables, hangs a single steel sphere, 5.5 meters in diameter, painted in the gold color of the surrounding structure. Its weight, 728 metric tons. It hangs there permanently, 24 hours a day, 365 days a year, slowly shifting as the wind loads on the building change. There are hydraulic shock absorbers at its base, 8 of them, to prevent it from swinging so far in an extreme event that it damages the surrounding structure. During Typhoon Herb, one of the strongest storms in Taiwan's recorded history, this sphere moved a full 1 meter in a single swing. Engineers monitoring from the observation deck watched a 728-ton steel ball shift through the air above them, silently in the opposite direction to the building around them. The result, a 30 to 40% reduction in sway under extreme conditions. The building still moved, but within the human comfort threshold. The occupants felt nothing alarming. Taipei 101's pendulum sphere is the most photographed example, but engineers have developed multiple approaches to the same fundamental principle, each adapted to the specific geometry and resonant behavior of the building it protects. The Shanghai Tower, at 632 meters, the second tallest building on Earth, uses a suspended mass of approximately 1,000 metric tons, the heaviest passive